So as we've discussed over and over again, one of the big mysteries in early chemistry, and one that took decades to really get our arms around, was why are the properties of compounds so different and so seemingly unrelated to the properties of elements that make them up. We've talked about the classic example, sodium chloride, which seemingly has nothing to do in terms of its properties with the elements that make them up. Reactive sodium and toxic chlorine gas. Another great example written about in the course platform and the launch here is mercury oxide. So mercury, as you may know, is a liquid at room temperature, melts from a solid to a liquid at negative 38 degrees Celsius. Oxygen, a gas at room temperature, melts from a solid to liquid oxygen at negative 220 degrees Celsius. But mercury oxide has a melting point of 500 degrees Celsius. So again, another example of a compound, we'll go over and over again, copper sulfate, zinc sulfate, look nothing like the elements they're made up of. Another example of a compound which bears little resemblance to the elements that make them up. So as I alluded to before, sometimes when the answers are seemingly super elusive, hard to come by, sometimes the best thing to do is just study that what you have in front of you and see if you can document some properties of whatever you're looking at and then see if patterns emerge. And so we've actually done that already with the metals. We built up a chemical reactivity series of the metals. We talked about in one of the course platform write-ups the reactivity series of the halogen gases, so fluorine, chlorine, bromine, and iodine. And so we have, we're building up a detailed set of properties of the elements. So pretty good progress thus far. Another key observation that we made in chapter 3 is that for some reason, when you use electrolysis, when you run electricity through solutions, it's easier to separate out or break apart less reactive elements than it is more reactive elements. So when we run electricity with a 9-volt battery, we can collect copper, we can collect zinc, relatively unreactive metals. We would be able, as I mentioned, be able to pull out gold from solution or silver from solution, but we will not be able to pull out, with at least our 9-volt battery, more reactive elements like sodium, lithium, potassium, strontium, calcium. Very much related to this is an observation that certainly didn't elude thinkers and philosophers from ancient times, was that some of these very non-reactive metals exist in their pure form. So even though gold is a relatively rare substance on Earth, there's way more sodium on Earth than there is gold, you will never find a pile of sodium in a mine or out in the woods or in the desert when you're just kind of walking around. But in history, we have found gold just by itself in the woods or in nature. And so that's another unmistakable related idea. So we can electrolyze and separate out non-reactive elements, and we can find actually non-reactive elements in nature. So there must be some connection there. So what this all suggests is that less reactive metals are less likely to form compounds, and more reactive metals are more likely to form compounds. Now, as I say that, it almost sounds like super obvious. Of course, more reactive metals are going to react to form what? To form compounds. But herein lies a potential relationship between compounds and elements to be discovered. Is there a relationship between the chemical reactivity of compounds and the chemical reactivity of the elements that make them up?